Good afternoon to you all. My name is Ilaria and I'm a member of We Science at the Bergamo Scienze Festival Youth Group. Before starting, I'd like you to focus on the fact that connecting to bergamoscienza.it and clicking on the live button, you can post on Facebook and Twitter the live streaming of the event and send questions to speakers or invite your followers to follow the conference live. The questions from the web are collected by us, the volunteers, and we're selecting a few of them during the question and answer session. For simultaneous translation, you can scan the QR code that you see projected behind me. The QR code will directly address you to Converso web app, where you can select the interpretation language from the scroll-down menu. To listen to the translation service, you need earphones. You're kindly asked to use your own. Should you not have one, you can ask the volunteers in the room. I'd like to welcome you to today's event, whose title is The Science of Light, from Galileo to Quantum Physics. We are pleased to host Serge Haroche, Nobel Laureate for Physics in 2012. The conference will be moderated by Dario Menasce from the National Institute of Nuclear Physics. We invite to introduce the last conference of Bergamo Scienze Festival, Mr. Galandis, who is president of ST Microelectronics. You are kindly asked to mute your smartphones and to take part in Bergamo Science's initiatives. Thank you very much for listening and enjoy the conference.
Buonasera a tutti.
Good evening to you all. It's not easy to open such an important conference. From Galileo to quantum mechanics is a long journey, a complicated journey, which is driven by the wish to understand and to solve problems. A journey that is based on methodology, curiosity, intelligence, hard work, that brings us to the scientific world, which is so interesting, which has also very many spin-offs. Now I'd like to show you one. There are many, but I'll show you one. In the Second World War afterward period, some scholars were trying to improve the way to communicate between the United States, America, and Europe. And they found a transistor, weird device. It was back in 1948, in 1936, the transistor was the device some people were awarded the Nobel Prize for. And then the chip was discovered. Since then, we went a long way. Today, leveraging on science, light properties, we can build very small transistors. We manufacture 100,000 times thinner than human hair, more than 1 million in square millimeters. They are all beautiful. We make a mistake once every 2 billion chips. This thanks to methodology and science, but this is not enough. To allow for better communication, you must build these devices, but also have and develop the software to allow them to work. And given that we are in Bergamo tonight, the fundamental algorithm that allows all the devices in our pockets, allowing us to communicate on a daily basis, is called the Viterbi's algorithm. Mr. Viterbi was born in Bergamo on 9 March 1935. So since then, from scientific discoveries, we are here today with today's applications. So hopefully my words encouraged your curiosity, showing you how from important ideas you can develop important devices that have an impact on our daily life. That's all. I'd like to thank the organizers of this beautiful event and enjoy this journey. Thank you. Does the microphone work? Can you hear me? Yes. Thank you for coming. I'm very anxious to introduce Professor Haroche, Serge Haroche, who is a French physicist from Casablanca. He was awarded Nobel Prize in 2012 together with the U.S. scientist Wineland concerning the discovery of experimental methods to measure and manipulate individual quantum systems. This means this gentleman was capable of manipulating single atoms in the first time for mankind, when 100 years earlier we didn't even know that atoms existed. He was a researcher, a teacher and mentor for many scientists who are working across the world today. So a person whom, like many other renowned scientists, left a trail behind him. As Newton said, what a scientist does, it is because it is walking on the giant's shoulders. He's also a writer. Recently he published The Science of Light, from Galileo telescope to quantum physics. I am modestly an experimental physicist. I work at CERN, Geneva, and I participated in the discovery of Higgs boson. We'll have a very pleasant conversation with Professor Haroche. I read your book and I advise this book to you all because this is a treasure trove of information, and I decided to follow the pattern that the professor gave to his book. He started off by describing his youth, how he began his career, what were his first steps in science, and these first steps also coincided with key technological innovation. When he was a boy, at that time, the first lasers were being built, lasers that have had a huge importance in our daily lives. So I'd like to ask Professor Haroche, how and why did you start this career? What were the passion, the underlying passion, the motivations why you became a scientist? We are all scientists, we are nerds, and we are all very passionate and curious to know things. This is what I'd like to know from you. Why did you and how? Because you started.
First of all, I would like to apologize for speaking in English to Italians and to have to receive the question through translation from Italian to English, but this is the way science is working. It's an international activity, and the language, which used to be Latin a few centuries ago, has become English, and so we have to accept that. And so the question about why I was interested in science from the beginning, I think my first interest was in mathematics. As I was a high school student, I was very much driven towards geometry and algebra, and I was amazed by the fact that physical phenomena could be explained by mathematics. In fact, this has started at Galileo's time. I think Galileo was the first scientist who understood that the world was written, was explained in mathematical terms. And this is really fascinating, and I think it's a very deep question. Why mathematics, which have been invented by the human brain, are so well adapted to explain the world around us? And my first, the first kind of observation which are related to mathematics is astronomy, the motion of the planets, the motion of artificial satellites. In fact, when I was young, it was the beginning of the first satellites were launched, and it was the beginning of the race to the moon. this was fascinating. This was a kind of exploration which could be understood and explained by mathematics. So from the beginning, I wanted to do physics and to use mathematics to explain, to try to understand the physical world. And then I went into École Normale Supérieure, which is a school where I was accepted to be trained in science, and I was exposed to very charismatic teachers who told me about atomic physics. You know that an atom is a system in which electrons rotate around the nucleus. This is a small planetary system, and so the laws of mathematics also apply for the system, but the laws are very different from the one we are used in the macroscopic world. And so I had to be familiarized with the mathematics which were useful to understand the microscopic world. And I was fascinated by that too, because it's again a field in which by mathematics you can understand the world at the micro scale. So because of the connection I had with this masters, Claude Cohen-Tanuji was my thesis advisor, Alfred Kastler, who was also a very important physicist at that time, I was directly driven towards this kind of physics. So this is, so to speak, by luck, by chance. And the other luck I had, which you mentioned, is the fact that I started this at the time when the laser was invented. And the laser turned out to be a fantastic source of light, completely different from the light of ordinary sources like the sun or the lamps in this room. And we understood at that time that the laser would be a fantastic tool to make new discoveries in basic science and in applied science. And in fact, all our dreams have been completely, in fact, we could not imagine all what the light would, all what the laser would bring. We had some dreams, we had some kind of ideas, but the reality, what really happened during the last half century, was much beyond our dreams, and we may speak about that later, but the laser has turned to be one of the very great inventions, great discoveries, which have changed our technology. In the introduction, it was alluded to the transistor and to the computer, which is also another very big discovery and invention of the last 60 or 70 years. And if you combine the computer and the laser, you get the internet, the network of communication in the entire world, which has changed our way of living. And all this has come from discoveries which were made at the beginning to understand what light is about. And this gave me the idea to write this book to show how the history of the science of light has accompanied the development of science in general. The scientific method, the rational scientific method, which started at the time of Galileo and Newton, have been triggered by our wish to understand what light is about, what the interaction of light with matter is about. And I think it's a fascinating story which links us, as you said, to the giants which have started this big revolution 3 centuries ago.
Molto interessante lo spunto.
Very interesting. You spoke about discoveries because Professor Haroche said that you initially were interested in mathematics and physics. To many people, mathematics and physics are the same thing, but they are very different things because mathematicians investigate his or her own reality, posing hypotheses and taking then logical conclusions out of this. He may well sit in a dark room and be a mathematician, while by the same curiosity mathematicians have, but physicists ask nature first, observe nature. Mathematicians do not dirt their hands, while the physicists go into the mud and starts observing the world, and from this observation he or she extrapolates ideas, concepts, develops theories, relies on mathematics. So mathematics is much more than physics, and by using mathematics he or she produces predictions that must be compared with nature itself. It is nature that has the final saying. So I suppose, Professor Haroche, that when you were you considered the mathematical aspects and were driven by curiosity to put your hands on nature, to ask nature first, so to become more hands-on.
Yes, I think what you say reminds me of a discussion I had with my fellow students when I was studying physics and mathematics. In fact, I had colleagues, young colleagues, who were much brighter than me in mathematics, abstract mathematics. They were able to understand and even to invent theorems which I was completely unable to do. So I decided that I would prefer to stick to the mathematics which were useful for physics and to use mathematics to understand the world. And when I discussed with them, I told them what you just said, that in fact a physicist is obliged to take into account what nature tells him or her. That is, you have observation, and the math that you are using have to help us understand the world. So we are constrained by reality, whereas an abstract mathematician is not constrained by reality. He can elaborate theories which do not have any foot into the real world, and which is also beautiful. And I think it's a completely different kind of knowledge. And what I find mysterious is that even mathematics, which were invented just out of curiosity by abstract mathematicians, proved later on to be useful to understand the world, to understand the physics. It's a case in quantum physics. The quantum physics is based on an abstract theory called the Hilbert space, the theory of the Hilbert space, which describes how mathematical objects relate to each other. And it was invented by Hilbert at the beginning of the 20th century, by a mathematician who had no idea that 20 years later, his theory would be the basis of quantum mechanics and quantum physics. And now, the objects that we are dealing with in quantum physics, atoms, simple quantum systems, are described by a mathematical object called a wave function, which obeys to the laws of Hilbert, that Hilbert had developed. And this is, for me, it's mysterious. I don't see this direct connection and how it happened. It cannot be a coincidence. There is something very deep in the fact that the physical world is described by mathematical laws.
Sì, è uno spunto molto interessante questo fatto che
This is a very interesting insight, the fact that math and physics somehow run along independent rails that sometimes have a meet, because mathematicians don't need physics, but the other way around is true. And sometimes a mathematician will develop some mathematical models because driven and inspired by some symmetries they find in nature. So I think it's a very interesting dual role. I thought I would split our conversation into more human-related aspects, but sometimes it's also nice to talk about technology. We mentioned the laser, which is a fundamental tool for your research. Professor Haroche, would you mind, Professor Haroche, to spend a couple of words to explain what a laser is, how it works, why is it so important both for research and industrial applications? The man of the street will only see the relevance of technology applications, but I think that equally important are also scientific applications which will drive new discoveries.
In order to try to understand in qualitative terms what laser light is and how it is different from ordinary light, we have to say a few words about light itself. Light is an electromagnetic wave. It's a wave, it's an electric and a magnetic field which propagates through space at the velocity of light, very, very fast. And it is described in the 19th century, it has been described by Maxwell, in Maxwell's laws of electromagnetism. The light that we see is only a very small window in the spectrum of electromagnetic waves. This is a light to which our eyes are sensitive, and this light oscillates very, very fast. The number of oscillations in 1 second is hundreds of thousands of billions of oscillations per second. So it's extremely fast. Now you have slower waves, which are called radio frequencies, infrared light, and you have faster waves like X-rays or ultraviolet light. And so we see with our eyes only a small window in this spectrum, but the other waves also exist, and they are detected by other kind of devices like infrared detectors, radio wave antennas, and they also provide very important information about the outside world. The radio frequency wave, which are detected in radio astronomy, tell us the story of the early universe, for instance. So this light, the natural light, is random. By random, I mean that the atoms which emit light emit it in all directions with a wide spectrum of frequencies, and it's also incoherent in the sense that it does not oscillate regularly. It oscillates, and at some time you have jumps in the phase, and it starts oscillating with another phase. So this is the natural light that we see from the sun or from the lamps. In the laser, all the atoms which emit in the source, which emit the radiation, all the atoms emit light in step. That is, all the light beams are in the same direction. The light is collimated, it's a very narrow beam, and it's also a very ordered beam. It's monochromatic, only one frequency, not a range of frequency, only one frequency. And it's also coherent. It does not skip a beat, it oscillates like your heart. You know, the heart is beating at a regular rate. Ordinary light would be like a heart which has problems, which is beating irregularly. And you know that when it happens, it's very serious. You have a disease. So the laser is like ordered light, which does not have these problems. And this light allows us to do a lot of things that ordinary light cannot do. For instance, you can do interferences with laser light. Interference means that if you split a light beam into two parts and then recombine them, send the two parts together, they will either increase the light intensity if the two beams reach their maximum at the same time, or they will decrease the intensity because one of the beams will be oscillating up while the other is oscillating down. So you will have dark and bright fringes, dark region and bright region. And this interference is very sensitive to difference in distances and allows to make very, very precise measurements of all kinds, and has developed a lot of apparatus which can measure distances with a very high precision, can measure time with a very high precision too. So we by domesticating light, I like to talk about laser like tamed, domesticated light, as opposed to the white light of ordinary sources. By domesticating light, we have been able to do a lot of fantastic things in technology that we might talk about. So basically, a laser is a source of light in which all the atoms are obliged to emit in the same direction at the same rate, light which is well controlled.
Quando abbiamo parlato, il professore ha parlato di onde elettromagnetiche.
When you talked about electromagnetic waves, Einstein discovered that light is actually consisting of particles. And that's when a very profound dispute was born about the dualism between wave and corpuscle or particle. For a long time, physicians were looking for philosophical interpretations to their discoveries. When quantum mechanics was born, then we're faced with something quite difficult to explain, and Heisenberg and Schrödinger had some very harsh disputes about the interpretation to be given. I mean, among the many mysterious causes of quantum mechanics, perhaps the most mysterious puzzle is the concept that the particle does not have a specific position in space. There is not this idea of having a precise location. It's always scattered in space. There are many things related to that. And as it were, the correct interpretation we should give is still susceptible to discussion. That's why physicians at one point said, shut up and compute, because quantum mechanics has some not well understood foundations. However, the theory is so precise, it allows us to make amazingly accurate measurements. Hence, I'd like to hear your opinion, Professor Haroche, about the relevance to discuss the very foundations of quantum mechanics, when it turned out that it was able to give us some very important and valuable information for our daily life.
Yes, you mentioned a very important point about quantum physics. In my previous answer to your question, I said that light was a wave, and in fact, this answer seems to be the end to the old dispute between the 17th century between Huygens, who said that the light was a wave, and Newton, who said that light was made of particles. In fact, Newton did not believe in the wave aspect of light. He said that light was made of bullets, like bullets, which were, when they were impinging on water, they changed direction, and he tried to explain the laws of lenses, the laws called the Snell-Descartes laws, which describe how light is deflected when it goes from one medium to the other, by telling that it was a particle, while Huygens gave the explanation in terms of waves. And in the 19th century, it seems that Huygens had won the battle, because obviously interference cannot be understood with the particle aspect of light alone. And then Einstein came to the conclusion that to understand some effects, like the photoelectric effect, the fact that when light impinges on a metal, it ejects electrons. The way these electrons are ejected happens to be due to the fact that you have small bunches of light energy which are absorbed in order to eject the electron. And if you assume that light is a wave, is a continuous wave, you cannot understand that. So he opened this, what I call a Pandora box, which is something which is full of contradiction. It's very difficult for a classical mind to understand that a wave can be made of particles, that particles have also a wave character. And this leads to the fact that you mentioned that in quantum physics, a microscopic particle, like an electron or an atom, does not have a well-defined trajectory. If you don't look at it, you have to assume that it goes through several trajectories at the same time. This is called the superposition principle, which is the basic principle of quantum physics. But this is quite counterintuitive for us, because in the macroscopic world, we never saw, for example, a ball going through two different trajectories at the same time. We don't even have the imagination to understand what it means. So it's a very strange law. It's what Bohr called the complementarity principle. He said that in some experiments, light behaves as a wave, and in other experiments, it behaves as a particle. And what makes the change is the kind of apparatus that you are using. In fact, the apparatus forces the system to behave either as wave or as particle. And this leads to another very important point, that you cannot describe a phenomenon without specifying how you observe it. The apparatus that you use to observe is perturbing the system in a way which will make the system appear as a wave or as a particle. So this is a modern interpretation of quantum physics, this duality, and Einstein did not like it, because there is another aspect which is important. The wave, in fact, is a probability wave. It's a wave whose amplitude allows you to compute the probabilities that a particle will be here or there. And so the quantum physics has renounced the determinism of classical physics. In classical physics, if I give you the position and the velocity of the particles, everything in the future will be possible to be calculated. In fact, Laplace a French mathematician and astronomer in the 19th century, said, if a demon can have the position of all the particles in the universe and their velocity, then it will be able to predict the future and to understand the past. And of course, this is not possible because there are too many particles to do that. But in principle, at least classical physics would allow that. Quantum physics tell you, even in principle, it's impossible. Quantum physics is random. The wave that is describing light or matter, because matter also is made of waves, this wave is a probabilistic wave, which allows you only to compute the probability of events. So it's a completely different world at the micro scale. And the problem, the big challenge is how can you use these very strange laws to build devices which will be useful in the macroscopic world of our everyday life. And we are starting to do that now.
Sì, questo è esattamente l'aspetto fascinoso.
And that's exactly what fascinating research, Professor Haroche, because at the beginning of the 20th century, a major split was made vis-à-vis the previous world. In the previous world, the physicians were dealing with something that could be touched or seen. They were dealing with practical objects. With the advent of quantum physics and mechanics, abstract events came about. When we talk about Schrödinger equations, amplitude of probability, we're talking about something a physician can even visualize in practice. So this split has increased over time. Back at Fermi times, it was still possible to understand the whole experimental theoretical physics, or at least Fermi could. I couldn't. But it was in principle possible. Now the world of theoretical physics deals with very abstract concepts, concepts for which us experimental physicians, including you, Professor Haroche, find it difficult to approach. So a major divide and split was created. Professor Haroche, do you feel uncomfortable too sometimes when you need to discuss, to have a confirmation with a theoretical physician on a totally different plane? I mean, I'm retired too now, but remember back then when I used to engage with a theoretical physician. Now I find it more difficult. Perhaps I've grown older, but now it's too much abstract for my taste.
Yeah, I understand what you mean. The fact that we are not used to see directly this phenomena, but you can do experiments, you can develop experiments in which you can observe single particles. For example, using laser light, if you're in a very good vacuum, you can hold single atoms in what is called a trap, an atomic trap, with electromagnetic forces. You keep the atom still, and we shine light on a single atom, and the atom is emitting light, and you re-excite it and re-emit light and so on. And since this cycle goes very fast, a single atom can emit millions of photons that you can see even with your naked eye. So the atom appears as a small bright spot, but it's a single atom. And you know that it is a single atom because when it jumps from one state to another one, the light is going on and off. So what was predicted at the beginning of quantum physics by Niels Bohr, what is called a quantum jump, the fact that the atom is jumping from one quantum state to another one, is now something that you can routinely observe in experiments. So these are not like the experiment in high-energy physics, which require huge apparatus to accelerate particles and to observe them in colliding beams and so on. These are tabletop experiments that you can do, and you can see particularly with your naked eye, you can see single atoms, you can manipulate them, put them close to each other, see how they interact. And then when you do that, you see the laws of quantum physics, so to speak, in action. You see sometimes that the atoms behave as interfering waves, sometimes they behave as particles, well-localized particles, and it depends on the apparatus that you are using to do the experiment. And so I must say that as an experimental physicist working in this low energy tabletop kind of physics, we can acquire the intuition of what is going on. Even if it's surprising with our classical brains, we can predict what will happen when we do this or that experiment, and we gain an intuition which at least allows us to try to invent new devices and to put this system into situations which might be useful maybe for applications. But I must add that when we started, we did not do that because of possible applications. We did that as a challenge. Is it possible to do that and to observe single atoms? What will happen if we try to do that? So this is basic science based on pure curiosity. And if applications come, they might be surprising and they will come much later. And this is another issue that I think is interesting to talk about. It is a connection between curiosity-driven basic science and applied science, which is driven to achieve a goal and to make, if possible, a marketable product. And the laser has been very successful in this field. The laser has started a market of billions and billions of dollars each year. So people who had invested into laser physics to gain money have been very successful. And now there is a lot of startup companies which are starting to try to exploit this manipulation of single atom and single particles to design, to invent new devices which would perform things that was impossible to do before. But again, this was not my motivation, and one should separate basic science, which is driven by curiosity, and applied science, which is driven by the laws of the market and by the financial constraints. And this is a very important point, and I think both have to go together. And it is quite clear that if you don't have basic science to start with, you will never have applications. On the other hand, if you want applications, you need to have a kind of fertile ground on which basic science have opened different possibilities for application to strive. So it's a complicated connection, and the people who give money, that is the politicians, the governments, and behind them the society whose tax money is used to do science, should understand the importance of basic science and the importance of this connection between basic science and applications.
Sì, questo legame che c'è fra...
This connection between basic physics and applied physics is something troubling families as well. My wife has been complaining for all our life that I should be making money inventing machines against the cellulite or teletransportation. We keep discussing on this because she cannot understand that I study things that have nothing to do with our daily lives. Then you discover that what physicists do has applications, as Professor Haroche said. He was awarded Nobel Prize because of this. So everything is driven by personal curiosity, the wish to find answers when the questions are weird. And this then in the future might bear fruits. And this brings me to another issue. You mentioned how it is important for politicians to understand that they have to fund basic research, basic science, because then there are technological spin-offs. But after COVID, we have been witnessing to a lack of esteem by politicians and even by citizens with respect to science. There is a sort of distrust. Was this something that you perceived in France as well, or is it just something specific of Italy?
Yes, we perceive that, I think, everywhere. And at first, it's very puzzling, because if you think about it, we live at a time when science has never been as successful and has never been progressing so fast. What the technological world in which we live today has nothing to do with what it was even 50 or 60 years ago. 50 or 60 years ago, we did not have the internet, we did not have the GPS, we did not have magnetic resonance imaging, We did not have fast computers. All what we do today as if it was granted was an impossible dream. And so everybody has taken that as a normal gift without understanding that it is due to science. And paradoxically, it has led to a kind of distrust in science. And the reason for that is quite difficult to grasp. Maybe my interpretation is that it might be due to the fact that science is a global adventure which brings all the world together. So it's a part of globalization. And globalization is seen also as a threat to people who are left on the side of the road.
Yes.
And so you cannot use science as a way to bring some communities together, because science is a kind, give you universal truth. It tells you things which cannot separate people from each other. And people, for kind of tribal or community-driven reasons, want to belong to a community which separates them from others, because that makes them feel safer. Religion is like that. If you believe in some god or some religion, you are separated from others, and we see how tragic it can be. But for the people who belong to that, it's a way to feel more secure, because they can communicate with others, they can share. And the people who are against science use these anti-scientific and these conspiracy theories to bring themselves together in small communities. And this is dramatic, this is very bad, this is very dangerous because it leads to a lot of bad things that we know are happening. But it's a kind of perverse consequence, perverse result of the universality of science. Science is not something that you can use to protect yourself from others. Science is the common ground on which everybody should, on which everyone should agree, and it's not the way it works. And I don't know I think the only way we can do to prevent that is to elevate the level of education from very young children to university. More people will understand the value and the universality of science, the further away we will be from these problems. We need to really to improve the knowledge of the values of science, and I am afraid that it's the case in France that very few politicians have been trained in science. In fact, they don't know anything about science, and they feel, to some level, threatened by science, because it's something which escapes them, and they accept the idea that science is important. They will just tell you that it's very important, but when actions have to follow these very general sentences, they don't follow. Another reason is that science evolves at a very long time scale. You need, from basic discoveries to applications, sometimes you have 30, 40, 50 years of development, and politicians cannot wait so long. They have, in democracies, they have a very short horizon, which is the next election, and if they put money into science, they will not put it in other fields. It's true for science, but for instance, if you think about the climate change issue, it's the same. If a politician makes a decision to fight against climate change, the result will come in, let's say, take at least 10 years. In 10 years, the politician will no longer be in power, except if it is a dictatorship. And this might explain why, for these long-term issues, dictatorial regimes have an advantage over democracies, because the leader can think about a longer time scale, which will personally be important for him or for her. So it's a discussion which is interesting, and I don't know what is the solution, but I think the mismatch between the time scale of politics and the time scale of science is one of the big issues, which is different from the problem of fake news and all these other things. I just want to say, during the first campaign that Trump made to be elected in 2016, he used to say, "I love uneducated people." And this is very revealing. It means that he understood that if people were educated enough, they would have critical judgment, which will allow them to understand that all what he said and all what he promised was nonsense. So the connection between the lack of confidence in science and the fact that you have demagogues and populist people who come into power is in some way related, and we saw that for the COVID crisis, the fact that this anti-vaccination trends were developed in countries with people like Trump and people of this same kind of political ideas, if you can call that ideas.
La cosa incredibile è che noi viviamo nel
Incredibly enough, we live in the country which was the land of Renaissance, where artists and scientists were the same people, and the value of scientists was highly considered, as artists were highly considered. And the tragedy developed in 1910 in Italy with the Gentile reform, where separation was developed between humanities, culture, and techne, science, something that is done by engineers building bridges. So hence the distrust towards science, and this has been accelerated over the past few years. To go back to more scientific problems, not political ones, Einstein was the father of quantum mechanics and also of general relativity, lasers, whatever. Einstein is a scientist we have all been admiring so much. But now we have come at a crossroads, because quantum mechanics and the theory of general relativity describing two different worlds, so one microcosm and the other macrocosm, until now did not necessarily need to coexist or agree, because microcosm and macrocosm lived on two different levels. Now that we discovered the black holes and coalescing black holes, we have come at a point when these two theories must agree, must be reconciled. They must provide us with a consistent explanation, and they all both come from Einstein's mind. Will quantum mechanics encompass general relativity, or the opposite? This is something very fascinating to me.
Yes, it's fascinating, but I want first to reflect on what you said at the beginning about remembering the Renaissance time. And you said that it was a time when not only science thrived, but also the arts. And I think there is a very deep connection between the two. And the artists and scientists are both working with creativity and imagination, even if it's not used in the same way. And if you look at the evolution of art and science in history, you see that the big revolution occurred. I don't think it was a coincidence that you had big revolutions in art and in science coming together. You mentioned the Renaissance and the beginning of the 20th century with quantum physics and relativity on one side, and then the abstract art, the atonal music, the cubism and the expressionism in art and in music, in painting and music, came at the same time. And if you think of the atmosphere, the cultural atmosphere in Berlin after the First World War and before the Nazis came into power in the 1920s, it was a fantastic time for art and science and philosophy together. And I think this is very important. And this is another reason why we should do basic science. Not only because it might be useful, but because it's a part of civilization. We want to acquire knowledge in the same way as we want to develop new ways of expressing ourselves in art. It's a natural aspiration of mankind, and it goes together. So now, what you mentioned, the big question in the future is, of course, how to reconcile quantum physics and general relativity. General relativity describes how big masses of matter interact with each other through the laws of gravitation, and there is no quantum theory of gravitation. There is a quantum theory for electromagnetic forces, like you see that they exchange photons, and this is what makes charges attract or repel each other, but there is no equivalent theory for gravitation. What is the hypothetical graviton, which will carry the gravitational force, has not been observed, and one makes the hypothesis that it exists, but there is no direct observation, there is no theory to describe it. And as you said, it's very important to develop such a theory because the macroscopic world, the cosmos, and the micro world are connected together. If you want to understand the beginning of the universe, you have to understand the quantum phenomena which occurred at that time. And if you want to understand what happens in a black hole, you have to understand what happens to matter which falls into the black hole, and then you need a quantum theory of gravitation for that. And so there are big mysterious questions now, and you need a new Einstein, or we need new experiments which will, like at the beginning of the 20th century, give us some hints about what happens. But it becomes very, very difficult because it involves energies which are beyond the capacity of modern accelerators. You know much more about this domain than me because I'm working in low energy physics, and what we are touching at here are things which happen in very high energy physics. So there are big questions open, and this is why I think this is fascinating for young people. If you want to start and you are very ambitious, these are big questions that the future generation will have to solve.
Questo concetto teorie fisiche.
This concept that physical theories must be solved leads us to understanding where it was being solved. In the past, we had the Alexandria Library that lasted for 1,000 years. Almost all Greek, post-Greek philosophers visited the Alexandria Library. It was a sort of intellectual centrifugal machine. What a renaissance was in Italy over the past few years. We were lucky enough as to have the establishment of CERN at Geneva, which is a sort of rebirth of Renaissance world, or the Alexandria Library. This is the place where all scientists go. Also, Professor Haroche oftentimes was lecturing at CERN in Geneva. So this is a key place where to be. And to go back to scientific education that you mentioned, I believe that this is the only way out of this regression we have been witnessing over the past few years. We must improve scientific culture in Italy, in the rest of the world, so school is key. Hence the role of teachers, of educators. What do you think is the role of educators, the importance that scientists like me, or you, mainly like you, because you are an important role model for young people, because young people want to get somewhere, and to be awarded the Nobel Prize is something important, not much for the award, but for the purpose that brought you there. So what do you think about the role of teachers?
I think the role of teachers, of course, is essential because they are framing, they are training the mind of young people, and everything follows from that. If you have a generation of young minds who are well educated, all hopes are possible. If you have a generation of young people who get a bad education, a very low-level education, then you will have all the problems that we mentioned before. And so the problem, but if you want to have good teachers and dedicated teachers, they have to be recognized as people who are the most valuable in a given society. And this is not the case. An engineer is making much more money as a teacher. If someone is gifted in mathematics, if he goes into a private industry or if he goes to a company, he will make 10 times the salary he would have as a teacher. So this is just as simple as that. If you want to have a good education, you have to train better teachers. You have to attract into education gifted people, people who could make a difference. And so, but this involves a lot of money. It means increasing the salary is not by 3 or 4%, but doubling or tripling the salaries of teachers. And of course, if you say that, immediately the politicians will tell you that's impossible because of all the constraints that we have in society. What we say about teachers is also true about doctors, about nurses. So you have to, depends where do you want to put the money, where do you want to put the financial capacities in a given society. But I agree that if you want to improve the level of education, you have to improve the status, you have to improve the recognition of teachers in society. It was the case 100 years ago. The teachers were much more appreciated than they are now. In France, it was the case when the Third Republic started at the end of the 19th century. The teachers were called les hussards de la République. That is, the people who were here to create generations of people who would be good citizens of a republic, good citizens who would be able to vote in a way not for populists, not for people who say lies to them, but would be able to understand what the problems are and vote consequently, which is an ideal situation. And for that, you need a good education, not only for science, but for everything. And this is a big issue. I think there are some countries which have been very successful for that. For example, if you think about South Korea, in the 1960s, after the Korean War, it was a very, very poor country. It was very poor, and then they decided to improve the level of education first, and they founded schools for teachers, and which gave to these teachers the status of engineers. When they get out of these schools, they had the same kind of salaries that engineers had in other fields, and this has led to South Korea being one of the driving countries for innovation, for big technology and big industries. And other countries like Colombia, Argentina, which had the same possibilities at the start, have not developed in that way because they never raised the level of education. So there are solutions, there are examples. In the past, we have to do something, and at a different level. This is another issue that we discussed before this talk. In Europe, if you want to avoid the brain drain, the fact that bright young people go abroad to fulfill their aspiration, to do things, to do research, for instance, you have to improve the level of education, you have to improve the salaries, not only of the teachers, but also of the young scientists, because young scientists are driven by passion, but up to a point. You cannot use this passion just to force them to stay in a country which does not give them the possibilities to do what they want. And I cannot accuse young scientists to go abroad, to go in countries where they're paid much better, because you have only one life, and if you want to fulfill your aspiration, you go where you can do it. And this is the duty of countries like France or Italy, to create conditions which will allow us to keep our bright minds here, to do science here.
Mi piace molto questa conclusione, stiamo arrivando alla fine.
I love this. I love your last final words, and we are approaching the end of our time.
Mi piace molto l'intervento, l'applauso del professore.
I loved what you said in favor of teachers. We're talking about the lack of trust or lack of esteem towards researchers, but everything starts from teachers. They're underpaid, they're not given the credit to be the makers of culture, but they are the very pillar of future generations. That's why I really appreciate your words of praise. And this takes me back to the beginning of your book and your life, namely, what is science driven by? A scientist does not pursue money, but pursues his interest, curiosity. That's a real driver for all discoveries and developments in society. That's why it's a pity. I mean, I'm not talking about you if you're here because you're interested in this, but for many people, this is almost irrelevant, and that should worry all of us. Thank you so much, Professor Haroche, and we'd like to thank the organizers.
Il professore adesso interroga scritto e orale.
And Professor Haroche will be questioning you from the audience, both written and oral. No, of course not. Just joking. If there are questions, I think there is a question over there. I have a question. You were talking about teletransportation as a joke, but in recent years, we heard a lot about quantum transportation. What does it mean? And when do you think it could turn to something more real?
Microphone.
Yeah, you allude to what is called quantum teleportation. I think the cleverest thing about that is the invention of the word. The scientists who described this quantum process called it after this Star Trek, after this science fiction television program, and so it had a tremendous resonance in the media. But in fact, teleportation is nothing but a quantum fax. You know, a fax machine, which doesn't exist anymore, was a machine in which you have written on a page a text, you put it into the machine, and the same page is reproduced elsewhere. And you can keep the original. Now, according to the laws of quantum physics, you could do the same. You take a particle which is in a given quantum state, and because it is entangled with another particle which is in another place, you can have a copy of the state here, there. The difference is that the original is automatically destroyed. So, in fact, in some sense, quantum teleportation is more dangerous than a fax. If you imagine, for instance, like in science fiction, that you put yourself in a machine and you are teleported elsewhere, if there is the slightest mistake in the process, not only you don't have a copy, but you are destroyed at the starting point. So I don't think that many people would accept to go into this kind of machine. But of course, this is a joke. You cannot do that for macroscopic objects. You can do that for objects which have a well-defined quantum state, that is either a single photon or a single atom. But as soon as you take a macroscopic object, you have a phenomenon called decoherence, the loss of this very complex quantum coherence, the fact that you have a phase, a well-defined wave function at a place, and this does not work. In fact, it's just a quantum process which might one day be useful if you can build a quantum computer, because you could transfer information from one point to another one, but it will never be something which will allow you to travel instantaneously from one point to another one. This will be contradictory, first with relativity. This entanglement and this quantum teleportation effect is not incompatible with relativity, precisely because the original is destroyed. If the original was kept, it would violate causality and it would violate relativity. So we have to live with the laws of physics which prevent us to travel faster than light and which prevent us to be teleported faster than light. So it's just, the word quantum teleportation was just a very cleverly coined name to make you dream about things which will never happen.
Visto che il teletrasporto è pericoloso.
Since teleportation is dangerous, since teleportation is dangerous, just focus on finding a cure for cellulitis. Thank you so much for your wonderful lecture. While listening to you, I thought of a question. The universe was born out of light. Man was born in the universe, and therefore man is made of light. Man has free choice, and the light behaves a bit like a wave, a bit like a particle, and we don't know why. Hence, this leads me to think that even within light, there might be things such as free choice. Perhaps we have free choice too. because that existed already in light in the first place. So that's why we enjoy free choice.
I think your question makes me think that there is, of course, one topic that we forgot to discuss, is the fact that light is necessary for life to happen. In fact, we need the energy provided by light traveling from the sun to the earth to make the condition for light to be possible on earth. And this explains, I think, why light was worshipped from the beginning of humanity. People have been worshipping the sun, worshipping light, worshipping the fact that light was coming back every day and every season. And this was a kind of knowledge about light, which is not scientific at all. This is something which was driving more towards mythology and religion. And the big change which happened in the 17th century was that light has been started to be considered as an object of scientific investigation. So this is a big difference. But of course, light is essential for all kinds of biological processes, the photosynthesis, the fact that living bodies transform light into energy for their own purposes is very important. And there is an aspect of that which is essential now today in the search for exoplanets on which light may have developed. I think it's a fascinating field of research now, also a field in which young scientists might get involved, trying to find life and maybe intelligent life elsewhere in the universe. And I think this is a fantastic example of curiosity-driven research, because we will never go there. It's quite clear that due to the laws of physics that I mentioned earlier, we will never be able to travel to other galaxies. We will never go at the velocity required for that. We will never be able to go beyond the light velocity, which will take millions of years to get to these places. And you will need, even to approach the velocity of light, you will need to consume a huge amount of energy, which is bigger than all the energy available on Earth. This means that we will never get there, but nevertheless, we want to know about what happens there. And this is, I think, the most illustrative example of the beauty of blue sky research, of basic science research, to understand how life may have developed elsewhere. And we will know that because we are developing instruments which allow us to analyze the atmosphere of some exoplanets. And if the atmosphere is, and the temperature is in the range which allows for life to develop, then this must have happened. So I think this is one of the fascinating topics, maybe even more fascinating than finding the connection between general relativity and quantum physics.
Se posso permettere, vorrei aggiungere un...
If I may, I'd like to add a word of caution. When we talk about the free choice of particles and waves, we're talking about a different level altogether. Particles and waves, even though they might look complex, they are indeed quite simple concepts, while the concept of free choice is much more complex because it deals with human mind, human action. We don't yet know what intelligence is, so we can't really talk about free choice at the moment. On top of that, these are two different fields of discussion. The methods of investigations are different physics than in psychology, say. We can talk about that, but we can't draw any conclusions. It's an interesting debate, but I have a caveat, a word of caution. I am studying engineering. And in January, I'm supposed to sit for an exam on quantum physics. Hence, I have a question for you as a student. Some words of advice to better understand this rather thorny subject. Perhaps you, as a Nobel laureate, would have a few more hints for me.
You want a lecture about quantum physics? Or what? there are very good textbooks. There is a very good textbook by Richard Feynman, who was one of the great physicists of the second part of the century. He wrote a textbook called Lectures in Physics, and one part of the book is devoted to quantum physics. And I found it was one of the books which really pushed me into this field. This course was given in the 1960s, I think 1965, in Caltech in the United States. But I had already some approach to quantum physics before, so I'm not sure that if you start in quantum physics, it's the best way to start. But if you are going to have an exam on quantum physics, I assume that you have had already some courses on that, and then Feynman give a very good, nice perspective. Not only in quantum physics, the books is fantastic because all fields of physics are touched, and in thermodynamics, in mechanics, in optics, he gives very original viewpoints, and it's a very, very interesting approach.
Sì, le Feynman Lecture sono sicuramente il massimo.
The Feynman lectures are actually the top of scientific education and literature. But when I was a student, Feynman lectures were very expensive, but at least I could go to the library to look at them. But then there was always a long waiting list. Now you've got a huge opportunity. The internet, on the World Wide Web, you find even too much educational material. And there is another trap. You need to distinguish then what's right and what's fake. The scientific method is quite rigorous, so the World Wide Web is fine, but you need then to be able to distinguish, to develop a critical judgment. And then if your professor will help you in that, all the better for you. Any other questions? Good afternoon. First of all, I would like to thank you so much, to congratulate for your clarity and also for the quality of the questions. We were perfectly in sync with this festival. I'd like to congratulate you both. In this dialogue, you talked about the difference between applied science and basic science, so theoretical science, and you emphasized how they were driven by different types of curiosity. The same can be seen here in Italy, so much so that Italian institutions have made huge efforts in investing in more technical schools, rather more theoretical high schools such as lycees. And that's why many students are attending technical schools. But over and beyond what the government has tried to do, I must say that the level of attractiveness is quite different. I mean, it's much more easier to have your curiosity piqued by something we can see that has industrial application, but it's much more difficult to be attracted by the atom applications, because most students are not aware of what atoms could be useful for. Here's my question. How can we grow and cultivate curiosity towards these issues? What advice would you give to teachers of various schools to be able to drive this curiosity in their students? What advice could you give to then teenagers? My daughter is about to pick university curriculum, and then it's almost a leap into the dark because theory is something they're not familiar with.
I think that it's not so difficult. Young children are fascinated by big questions. They ask all the time questions about the universe, about the world around them, about a lot of questions about astronomy, about astrophysics, about what atoms are. If you give simple answers to this question, you open their mind to fundamental issues, to fundamental questions. I got 60 years ago, I got driven to this because I was fascinated by astronomy. And I think now, for example, if you talk to young child about exoplanets. You explain to them the orders of magnitude, the fact that you have a huge number of galaxies, and in each galaxy, a huge number of stars, and around each star, a few planets. You can give them the feeling that there must be something, there must be life elsewhere, and you can try to explain in simple terms how you could detect this. So you can give, by answering simple questions, you can just nurture the curiosity of young children, give them very simple estimates, orders of magnitude, trying to give some examples, make some comparisons, and to make them understand that they would need some mathematics, they would need some way to calculate things, but it's not so difficult and it's not very abstract, it's not theoretical physics, it's something which is related to problems that they can grasp and that they can envision. And so I think, paradoxically, I think it might be easier to bring young minds towards science through basic questions than it is to bring them towards science by talking about specific inventions. So maybe I'm wrong, maybe it depends also on the personal development of each child. Some child will be inventive, would like to make some useful things, and some others would like to dream about more abstract questions. And this abstract question, you can make them also, you make them perceive that there is a simple way to address these questions and these issues. But the main point is to raise the curiosity for applications or curiosity for basic science and basic questions.
Sì, se posso aggiungere, curiosità è la chiave di tutto. Il problema è che la curiosità...
Curiosity is the key, but oftentimes curiosity is stifled in schools. I know that there are many teachers sitting in this room. If I were powerful, I would reverse the way in which physics is taught in schools, because first you must be fascinated by a subject, because if I explain black holes, gravitational waves, children will be fascinated, but if I teach vectors or derivatives, they develop no interest. Science and physics
La fisica poi ha bisogno.
Physics then needs plenty of rigor. It's like a boy wants to learn how to play guitar to attract girls. If he buy the guitar and then he needs to learn the theory of music, then he won't go ahead with playing the guitar. But if he starts by playing, then he'll overcome all imagination, all difficulties. So we kill imagination in young people when we teach things in schools nowadays.
It's a good metaphor.
Buonasera.
Good evening, Professor. This is a great honor for me to address you a question. From your perspective, given that you worked on aspects such as quantum decoherence, what is the current development of quantum computing, how you contributed to these studies, and what new generations of scientists could do in this field?
So, a quantum computer would be a device which would be able to do calculation by exploiting the principle of superposition of states. It would be a computer which would follow several passes at once, and in the end, by an interference effect, you would get the result of your calculation. And if on paper, in theory, it works, there are some algorithms which would be able to compute things, to solve some problems much faster than a classical machine. But as you said in your question, The big challenge is to overcome decoherence, the fact that as soon as you have a large number of particles, the coupling to the environment destroys the quantum coherence very quickly. And so we are in a kind of conundrum. On one side, we want to isolate the system completely from the outside world to avoid decoherence. But on the other hand, we need to extract information, so the system has to be open, at least open to the observer, which is the person who wants to get the information. And so this problem is very difficult to solve. Some people are thinking about error-correcting codes and developing codes to control decoherence and to correct for the effect of decoherence. It's a very complicated topic, and one has made some progresses in some aspects, but it remains, there is a lot of challenges which remain to be met. We have small, what I could call computer toys, a few tens of particles, which are called quantum bits or qubits, to solve very simple problems. But a machine which would be useful to become a universal computer would require to be able to control millions of qubits at the same time, and nobody knows how to do that. And it's a very competitive field, as you mentioned, and competition has good and bad aspects. The bad aspect is that as soon as a group or a company like Google or Microsoft is making a very small progress in one direction, they oversell it, they make a lot of publicity about it, and they start to explain that they have solved the problem, that the computer will be realized in a couple of years from now, and this is not true. It's a very long-term project. Nobody knows whether it will be successful or not, but it has just nurtured the imagination of a lot of people, and that's the way it works. There's another big project which will be even more useful for society if it came to fruition, is the nuclear fusion, the fact to have power plants which will produce energy not by fission, but as it is done in nuclear reactors now, but by the fusion of hydrogen atom to make helium, which is a process which works in stars. So to make an artificial star would be certainly something which would be very, very useful to solve the energy problems that we have to solve. And this is again a project which has started 50 years ago, and it might take another 50 years before it succeeds. So the quantum computer is a little bit like that. It's a long-term project, and in the way to build this quantum computer, we are achieving a lot of interesting research. We have what is called quantum simulators. Quantum simulators are small computers with a few tens or a few hundreds of particles, which allows us to simulate what happens in real matter by controlling everything much better than you can do in real matter. And in this way, we might one day synthesize new materials with interesting properties. For instance, superconductors at room temperature, which is another goal. And maybe something else will happen, I don't know. In fact, if you look at the history, the people who made the big discoveries in basic science had no idea of the application. For example, the people who invented magnetic resonance thought that it was just a tool which would be useful for scientists. And then MRI came, and it has revolutionized medicine and the medical diagnosis and medical research. The people who discovered the laws of atoms had no idea that atomic clocks one day would be used in the GPS system to localize ourselves on Earth with a precision of about 1 meter. And when Einstein discovered stimulated emission, he had no idea that one day there would be a laser. He died before the laser was invented. And so the I think the big difference today is that because of this access of the media and this need for publicity to raise money, the dreams of scientists are just publicized all over the world in a way which give hopes and which make people imagine things which might never happen. And this might backfire, because if in 20 or 30 years from now there is no quantum computer, then people will say, okay, we lost all this money in this research, which is not true, because other things will happen and other useful discoveries and other useful devices will have been developed in the way.
Se posso aggiungere un breve commento a questa domanda, porta dietro un concetto.
If you allow me, there is an important sociological concept. We are reaching the limit when technological development is becoming quicker than our ability to find applications to such a technological development. And this is interesting on one side, but also very dangerous. But quantum computers will bring us somewhere. We do not know where exactly. This is still an engineering time for quantum computers.
Ringraziamo gli ospiti di questa sera.
Let us thank tonight's guests, and we'd like to thank all of you for participating in this conference. And please remain seated, because as usual, we have the end of festival ceremony. That's why I would like to invite Nicola Quadri to come here on the stage. He works for Associazione Bergamo Scienza.
Buonasera.
Good evening, everyone. First off, we'd like to then give the Rita Levi Montalcini Lecture plaque to Professor Serge Haroche. Thank you so much.
Facciamo una foto.
Let's take a picture together with the plaque.
Grazie ancora.
Thank you so much once again. Professor Haroche, it was a real pleasure to listen to you and to translate you. Thank you so much, Professor Haroche, for speaking slowly.
Io prendo solo qualche minuto.
I will just take a few minutes. First of all, to thank you all for being here. This is the 21st edition. Last year's edition was called We're Growing With You, and I think that many of you have been growing in the last 20 years of our history. This year's theme was infinity and infinitesimal, as you can see on the background. It came from an insight of Gianvito Martino of the Bergamo Scienza Association. I think it does epitomize the meaning of this event. As you may have seen over the last fortnight, we have explored the world around us in all dimensions. We're talking about quantum mechanics, infinitesimal words, what happens in cells, in the DNA, whether we can manipulate it, what for. We've been talking about chemistry, living systems, ecosystems, plants, life in the oceans, and on and on. We went on talking about the whole planet, how it is doing. We've been talking about space explorations, astrophysics, gravitational waves. And that is one point. The other point I'd like to mention is that this title also encompasses many of the reflections arising out of engagement with the audience. We actually asked ourselves quite a few times whether there is a boundary to our knowledge or whether it's unlimited. The answer is for each of you. We know that science advances by small steps we can make together. And luckily, we are quite swift in our advancements. And the same applies to biomedicine, too, as we heard in the lectures devoted to health. And that's good, because it is true that we make only small steps, but we work together. And this title also reminds us that these orders of magnitude are not separate. We may have talked about quantum mechanics, astrophysics, physics and environment, but they are not unrelated. They're not decoupled. There are situations where phenomena are visible at different scales, where the release of molecules into the atmosphere does have an impact, and when an environment changes, organisms change, DNA changes, molecules changes. So the relationship between the local and the global dimension has been a topic in this festival for the last 20 years, and also the relationship we have with Bergamo. We invite scientists from all over the world, but then we also engage with the local population, students, schools, ordinary citizens. So that's why I would like to thank you once again for attending in great numbers. And just let me give you some numbers about the turnout. And then Alessandro Bettonagli will take the floor. In 2022, there were 74,376 presences in person. We have not finished yet. We've had quite a few events today too, but even as of now, we're over 81,000 visits, and we still have to measure then virtual connections, because we are streaming onto many platforms, including Corriere della Sera newspaper website. And I would like to invite Alessandro Bettonagli, who's the art director of the festival, one of the founding members. Please, Alessandro.
Grazie, Nicola.
Thank you, Nicola. Thank you all for being here. This time is my turn to thank a few people. As you can see from the screen, today is the 100th anniversary of Italo Calvino's birth. It is a quotation for Invisible Cities. Bergamo Scienza has been trying to be an answer for 20 years. During the opening, our chairman, Gianvito Martino, recalled the initial words of Aristotle's metaphysics. He reminded us how at Bergamo Scienza scientific knowledge is made accessible to a wider audience, not just as a result of cross-contamination, different languages, the rigor contest, but also thanks to the fact that information users are also information creators. Only by sharing this can we be innovative, can we have a broader presence, going beyond generations and disciplines. Only thus we'll be able to fulfill our innate need, as Aristotle put it, guiding us towards a real society of knowledge. Bergamo Scienza is accessible for free to a wider audience. I'd like to thank all people supporting the festival and the association activities, whether they work in public or private. They may be sponsoring, donating money. It doesn't matter how big or small they are. Here you see a list of our supporters and sponsors. And I'd like to invite Secretary General of Associazione Bergamo Scienza, Rosella Colleoni, and Umberto Corrado, who's one of the founding members.
These are the ordinary members of the association. Thank you to the sponsors and institutions that presented workshops at no cost, and Mr. Montrasio is invited on stage. Thank you. And to all those who have given us their time, their excitement, their passion, the We Science volunteers. Jacopo, Alice, Roberto, and Ilaria are kindly invited on stage. They are the coordinators of WeScience. I also would like to thank our steering board, which has been supporting us over these past few years. The scientific committee, Nicola Quadri, is invited back on stage together with Luca Perri and Katia Gissi from the Scientific Secretary. I really would like to thank her.
Scusate, mi hanno detto che ho saltato, vedete, anche leggendo salto i ringraziamenti.
I
Devo ringraziare le scuole
a few people. I must
dell'ufficio scolastico
thank
territoriale di
the
Bergamo.
schools of Bergamo, and I would like to ask the past president, Raffaella Ravasio, to come on stage. Raffaella Ravasio.
Per ringraziare insieme a me
To thank together with me the 63 Bergamo, Brescia, Cremona, Mantova schools, all the teachers and the students that developed 92 workshops of this 21st edition. Thank you very much for your work.
Volevo ringraziare anche tutte le
also
nostre
would like to
commissioni
thank
ed
all
invito ad
our
raggiungerci sul
commissions
palco i
and I
membri
invite on
presenti
stage
in sale dalle commissioni, comitato scuola, comitato organizzativo,
members
scienza,
of
innovazione e
these
COSI. Grazie
commissions.
ancora. Grazie.
Thank you.
Continuo con i ringraziamenti,
I
grazie a
keep
tutti i
with
fornitori
my
che hanno
thanks
contribuito al
to all
successo di
our
questa
suppliers
edizione,
that
gli
contributed to the
allestitori, i service
success
audio,
of
luci,
this
streaming e video,
edition,
le interpreti per la
the
traduzione
interpreters
simultanea
for
e quelle
their
del linguaggio dei segni.
simultaneous
Novità della 20ª
interpretation
edizione,
and the
fotografo
sign
Next
language
Station per l'ospitalità
interpreters
e il ristoro.
and
Grazie a tutti coloro che lavorano
to all
costantemente per il
those
festival, a
who have
partire
been
dalla segreteria
working for
dell'associazione.
this
Invito
festival,
Giuliana,
and
Greta, Paola e
Giuliana,
Sabattina
Greta,
a
Paola e
raggiungerci sul
Sabattina are
palco. Loro ci
invited on
seguono tutto
stage.
l'anno, perciò
They
la
have been
segreteria
following us
un bel applauso.
for the past 12 months, so it is 1 year work.
Ringrazio anche
I also would
la
like to
segreteria
thank
organizzativa del festival,
the
servizi CC, l'ufficio
organizational
stampa del Festival
secretary,
Delos, quello dell'associazione Studio Believe, il team comunicazione Studio Caffè, il Digital Advisor
the
e il
communication
coordinatore operativo Matteo
team,
Salvi che invito anche lui sul
digital
palco.
advisor,
Grazie.
and the coordinator Matteo Salvi, who too is invited on stage.
Ringrazio ancora tutti
I also
ed
would like
invito
to
tutti i
thank
nostri
all of
volontari,
you,
giovani e
and
senior, che invito a salire sul
invite
palco per
all
la
our
foto finale di gruppo.
volunteers to come on stage
viva Bergamo Scienza.
for
Continuate a
the
seguirci, vi
picture
ricordo la mostra
Long
dei
Life
laboratori.
to Bergamo Scienza, and you are invited to our exhibition.
Grazie
Thank
mille.
you very much.
Grazie ancora a voi
Thank
per aver
you.
partecipato,
Thank you for
così numerosi
attending.
a Bergamo Scienza.
Thank you,
E grazie ai nostri giovani.
and thank you to our youth team.
Dove ci mettiamo? Sono chiusi